let's regroup here. So let's hear what you guys said. So, Ben, what did you say the divergence test was about? What's that? Okay. More specifically, though. Yeah, sure. I am recording, yes, I am. Thank you for reminding me. Yeah. So it's more than that. Okay. All right, that's part of it. What else? Yeah. Right, exactly. So given a series, if that limit of the sequence doesn't go to 0, game over, right? Game over. This is going to diverge. So the sequence, the limit could not exist, or it could go to a non-zero number, and in any of those cases, the series diverges. So it's like you don't even talk about a series unless what? Unless what happens? That sequence does what? Not just converges to 0, right? To 0, because we're adding an infinite number of things together. The only way that has a chance to add up to something is if those numbers do what? Get super small, right? Get super small. Okay? What about if that sequence goes to 0? What's our conclusion about the series? Maybe. Still maybe, right? So those are the interesting ones, right? So the interesting series are where the sequence goes to 0, and now we have the question. Does the series add up to something finite, or does it still diverge? Okay? Geometric series. Geometric series. Trevor, what's that about? Given the general form, yep. It will go to 0 if R Good. Yeah. So if R is between -1 and 1, you got the AR to the N or the N minus 1. So that R has to be between -1 and 1. And then for this one, we actually can get the sum exactly really easily, right? We proved that it's A over 1 minus R. Okay. Ricardo, what's a P series? 1 over n to the P. What about equal to 1? No, what if it's 1 over n to the P and P equals 1? That's harmonic, right? So that's divergent. So yeah. So it's divergent from P between 0 and 1. Convergent for P greater than 1. If P is 0 or less than or negative, it's trivial case, right? Of course it's divergent. If it's 0, you're just adding a bunch of 1s together. If it's negative, then you have n to the positive P in the numerator, so it's not even worth talking about. It's divergent. But these are the interesting cases here. So when P is between 0 and 1, divergent, convergent for P greater than 1. When P equals 1, we know that is the harmonic series, divergent, right? So P series are interesting. Why? Because the sequence goes to 0 as long as P is what? The sequence goes to 0, 1 over n to the P as a sequence goes to 0 as long as P is greater than 0. So here are the interesting cases to analyze, right? Because all of these that I've highlighted here, for any of those values of P, the sequence goes to 0. It's just when P is greater than 1 is when it finally gets to 0 fast enough for the sum to converge, right? Comparison test. What's the gist of that? Corey.
All right. If you can compare your series
Yeah.
to a similar series that is divergent,
Mm-hmm.
if every part or every I guess subsequent addition of your series is larger than the one you're comparing to, then you know that your series is divergent. And if each subsequent addition is less than 1 that is convergent, you know that it must also be convergent. In the cases where that doesn't, those two things don't apply, then we're not sure.
Awesome. Well done. So it's divergent if it's bigger than a known divergence. And it's convergent if it's smaller than a known convergent series. But yes, what you said was all correct. So the given series, it's divergent if it's bigger than a known divergent series. It's convergent if it's smaller than a known convergent series. And so my little nutshell here is a sub n terms are all positive, right? So this is if all the a sub n terms are positive, that's the gist of the comparison test. Okay, it's the alternating series test. Adrian, do you remember? Yeah. Uh-huh. Yeah. Right. So yeah, exactly. Perfect. Yeah. So it's convergent if the positive parts of the terms, as long as they decrease to zero, decrease to zero, you get convergence. So this is worth comparing with the divergence test, right? We said with the divergence test, if it goes to zero, that's necessary, but not enough, right? So then what would make it enough? What's one way to make it enough, going to zero? Make it alternate, right? So if it goes to zero and it alternates positive, negative, then you're guaranteed for it to converge. Why? Because then every other term is decreasing the sum, right, by subtracting. Okay, questions on these. So the rest of the time we're going to work on the ratio test today. So questions on these. Yes, sir. Mm-hmm. Uh-huh. If you change so -1 to the n versus -1 to the n plus 1, just will switch which ones are positive and which are negative. That will never affect convergence or divergence. But it will just switch all the positive and negative terms. So actually, maybe this is a good time to let's look at the web work that you had, because there were lots to do with the alternating series. So let's glance at the web work real fast, and then we'll do the ratio test, okay? You ever hear that buzz and I forgot to get rid of it? Remind me. So, is that better? What number was it? You guys remember? 22. Oh, it looks like we got one to talk about there.
It's just because it added A as an answer.
Oh.
I didn't see that A
Okay.
was an answer.
All right, so this is a good one. Let's talk about this. So we see it's alternating, so it's an alternating series, but
You put C in thinking it's just convergent, and then you get it wrong and notice that.
right, but when you know you have only one chance, you read carefully, right? You read really carefully. Okay, so what is this really? 1 over n to the what? 3 halves, right? Okay, 1 over n to the 3 halves. So first of all, is it convergent or not? So we can apply the alternating series test, and we look at the positive part of the terms, and we ask the question, does it decrease to 0? Absolutely. So is this convergent? Yes, it's convergent. So now the question is it conditionally convergent or absolutely convergent? Meaning, right, absolutely convergent means if we took this series now, if it's the same series that didn't alternate, now we have to decide, if that's convergent, then our original series is absolutely convergent, okay? If this one's not convergent, then it's only conditionally convergent, conditional on the fact that it alternates. So What kind of series is this? P series, and P is greater than 1, therefore? So this one is convergent, therefore this one is absolutely convergent. It doesn't need the alternating effect to help it converge. That means it's absolutely convergent. Questions on that? So was that really the issue, was that you just didn't read fast enough?
Yeah.
What's that?
Yeah, or
What did I
just
say?
didn't read in general. Just kind of saw, oh, this converges, I'll put C.
Okay, okay. All right, let's look at one more. Any more questions about this one? So which one, 1 or 4? It doesn't look like we need, both of them you guys got, so let's just move on. Okay. Back to this. Okay, so let's review what the ratio test was. Remember what the ratio test was? You have an infinite series, and we're going to evaluate this limit. In a second, we're going to talk about what that limit's about. Okay, the limit of the n plus first term to the nth term, absolute value. And we'll call it the value of that limit L. And we said last time, if L is less than 1, then that series is absolutely convergent. If L is greater than 1, the series is divergent. If L equals 1, no conclusion, reach into the toolbox for something else. Is that consistent? Is this consistent with what we said last time? Okay. So let's talk about what this test is about. So this limit, why do we take this limit, and why do we have these conclusions? And it's something you all already know. So let's just see where this thing comes from. All right, so look at this first line there. Do you recognize what kind of series that first one is? You should see that's geometric. I've just changed A into C. So C for coefficient, okay? C for coefficient. And so what do you notice about from one term to the next? What do you do to one term to get the next term? What do you do? Every single time you multiply by R, right? So every time, so even the, so C to R to the N to C R to the N plus 1. You always multiply by R. And how does this thing converge when R is what? So it's like, you think of R as like a fraction, right? If we always are multiplying the last term by some fraction of what we had before, right? Then these are going to get small enough, fast enough for the thing to converge, right? So now look at any generic, so this is any generic series. How could we come up with, what do we multiply a sub n by to get a sub n plus 1? This could be any series in the whole world, and we want a general way coming up with, what do you multiply a sub n by to get a sub n plus 1? So like set that equal to x, okay? So what do you multiply a sub n by to get a sub n plus 1? X. What is x equal to? Yeah, you do. What is it? A sub n over. Okay. So in every series, what you multiply to get the next term is the ratio of the next one to the previous one. Okay? And so what do? We look at the limit of this multiplier, and at the limit of this multiplier, what did we say? When will it converge? When that limit is? A fraction, like R, right? So if the limit of these multipliers is converging on a value of R that's less than 1, right? If what you multiply by, like R, is converging to something less than 1, it's going to converge because basically it's converging into a geometric series. You see that? So if the limit of these is less than 1, say it's 0.7, okay, so say you get a limit of 0.7, then the multiplier from one to the next is getting closer and closer and closer to 0.7. It's basically becoming a geometric series with r equal to 0.7. So therefore, it's going to converge. You see that? So this ratio test is really just about is the series becoming a geometric series? Is it turning into a geometric series? Okay, so that's all that's about, because that a over a plus 1 is like a kind of a changing value of r. It's a changing value of r. If it converges on an r that's less than 1 or greater than negative 1, then it's converging into this geometric series. Pretty cool, huh? Okay, so let's do an example. Easy one to start with. So do this one. So what are we going to do? We're going to investigate this limit. Okay, and so before we start writing these out, especially when these get big and involved, it's a lot easier to start with this form. Do a to the n plus 1 times 1 over a to the n. Okay, that's the exact same thing, and by starting with it in that form, you make your life a whole lot easier, because then you don't have this gigantic fraction of fractions, okay, to start with. So you see how those are the same, and this is going to avoid, because if we wrote it like this, we'd have one fraction over another fraction, and then the next step we'd invert and multiply. So let's just start off by doing that, right? Make our life a lot easier. Okay, so infinity of, okay, so what is a of n plus 1? Or the n plus 1 term of this series is what? Negative 3 to the n plus 1 over n plus 1 cubed. And we're going to do times, all right, just the sequence itself flipped over, right? So 1 over a fraction is just you flip it over, right? So we then just go right to n cubed over . So that right there is equivalent to the ratio of a n plus 1 to a n. Just inverting and multiplying that denominator. Okay, then what we want to do, we want to simplify what's going on in there, and we simplify it by gathering the like things together, right? We're going to gather the like things together. So we want to gather the n cubed and the n plus 1 cubed, and then negative 3 to the n plus 1 and negative 3 to the n. Okay, and so then remember we learned the hard way on the quiz. What is the meaning of negative 3 to the n plus 1? What's the meaning of that? I know many of you. Manny, go ahead. No, so just we're going to pick n. We're not taking the limit yet. So n is some finite value. So what is negative 3 to the n plus 1? You're going to take negative 3 and do what? Yeah, go ahead.
Multiply it by itself n times plus an extra minus 3.
Right. This is the number of times we're going to multiply negative 3 together, right? This can save you memorization of rules. If you know what it means, if you forget the rules, then you can fall back on what it means, because it means multiplying negative 3 by itself n plus 1 times. And then what does the denominator mean, Hector? Okay, so if we got n plus 1 negative 3 is on the top, and n negative 3 is on the bottom, what is it equal to? What are we left with? Zoe, where? Where's the extra negative 3? Okay. We're just counting negative 3's. Where do we have one more negative 3? The top. So then we're just going to end up with negative 3, right? Because there's one more negative 3 up here than there is down here. So they can all cancel except there's be one extra one on the top. All right, and then we have this. We can just leave this as it is, and now we're ready to do the limit. Because when we did our sequences, remember, we practiced lots of limits like this when we did sequences. So what's the limit of this right here as n goes to infinity? Think of what will the biggest power of n be down here? It'll be n cubed plus yada, 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 right? So 1, right? So this limit is 1. We saw those when we did sequences. And then with the negative 3, just it's negative 3 as n gets big. So this whole thing equals to 3. If you just multiply that out, you'd have n cubed plus something n squared plus something to the n. But all that matters in a limit like that is the ratio of the. We're doing limits sequences like that. It's just one. It's a rational function. We did lots of sequences like that. So it's n cubed over n cubed plus something n squared plus something n plus 1. Remember that? Kind of. Yeah, so all that matters when n gets large, all that matters if the powers are the same, all that matters is the first. These just disappear compared to n cubed. So then we take the ratio of the leading coefficients. So that's just 1. That limit is just 1. Negative 3 is just itself. Absolute value is 3. Conclusion about this? Divergent. That's greater than 1. So what? So this is like a geometric series whose R value is converging to 3. You see that? So it's like when n gets really, really big, you basically get a geometric series whose R value is 3. And we know that that will diverge. Questions on this one? Okay, you guys get started on this. See how far you can make it. See if you can how far you can make it. Remember, start with this form, okay? A n plus 1 times the sequence as it is, just flipped, okay? That's going to save you a big writing headache.
denominators switch. So from the right side of the equal sign, those denominators are switched. If you go down below, I get to the when you have I get that whole thing perfectly, and then step
So
below.
now I'm just going to group the like things together. So I'm going to group the negative ones to the n. I just get one negative one. And then I'm going to group these 7n squared and that together. And then I'm going to group the n cubed plus 4 and that plus 4. You see, I'm just rearranging things.
Yeah, I was just wondering.
So you should have gotten to here. Now we're ready to evaluate this limit. So what's the biggest term of the top? 7n squared, right? And what do we have in the bottom? Limit is 7n squared over 7n squared as n gets big, right? Limit 1. Okay, biggest term up here, n cubed. Biggest term down here, n cubed. Limit is 1 times negative 1. Absolute value, limit is. Therefore, from this test, ratio test doesn't help. Ratio test doesn't help. So we reach back into the toolbox. Do we have something other than the ratio test for which we can make a conclusion here? So we say, is it a p-series? Is it geometric? Et cetera, et cetera. So what is it? What's that? Alternating series. And our alternating series test says? Yeah, so the positive part, so the Bn, right, the Bn is the positive part of the terms. As long as that does what, this thing will converge. Decrease to 0. Again, another sequence. So you see how knowing your sequences, how to analyze sequences is so important. Because now we have to analyze the sequence, 7n squared over n cubed plus 4. Does it decrease to 0? Because the power or the degree of the denominator is greater than the degree of the numerator, that thing goes to 0. Unlike the divergence test, with alternating series test, as long as it goes to 0 and it alternates, convergent. So then we say, so no, the ratio test yields no conclusion, but series is convergent by alternating series test. When you guys do written work on these, written homework or the test, you have to give justification. You have to give justification. So this would be the kind of thing we want. Show all the math that you do, show the math work you do, and then always give justification for your conclusions. Question on this example? Okay, so then, yeah, right, the ratio test only will tell us absolute convergence or divergence. It cannot tell us. So now, what about conditional versus absolute convergence? So 7n squared over n cubed plus 4. Okay, well, what we can do is we can think about what happens for large n. Okay, so what does this virtually become for very large n? Okay, but more specifically, how to, right? It's going to become like 7 over n. You see that? Exactly. So in the end, this is like 7 times the harmonic series for large values of n. So is this absolutely convergent or conditionally convergent? Conditionally. Needs, the harmonic series does not converge. So it needs the alternating effect to converge. So this is, so yeah, even better. So it's convergent by alternating series test, but it's conditionally convergent because 7n squared over n cubed plus 4 would diverge, right? Would diverge. It needs that alternating effect to make it converge. Other question? Yeah.
Can we take the limit of the positive part to infinity, but just stop before, where we would then divide both the numerator and the denominator by 1 over n squared, and then stopped before we would then plug in infinity to show that the limit is actually 0? Because wouldn't the limit as that approaches infinity be 7 over n in a sense?
Yeah, I think that's what I said, right? I mean, I think we're in agreement.
To show you that the limit as that approaches infinity becomes 7 over n, with limit notation in the algebra.
Yeah, at least so that, or just like a written explanation, or like a little sentence of what I said. Yeah. So you could just you could say as n gets large, this becomes like 7 over n. You could write that out if you wanted. Yeah. Or you could do it formally with algebra. Okay, other questions on this example? Very good. Let's do another one. Get factorials going here. Okay, Andrew. Tell me about n factorial over n plus 1 factorial. 1 over n. One over n? Yeah, because really n plus 1 factorial is the same as n plus 1 plus, or times, n times n minus 1 times n minus, which is just n factorial, right? So it's the same as n factorial, but then multiplied by n plus 1. So we get 1 over. And then 2 to the n plus 1 over 2 to the n. Right? You should see that as just a bunch of 2's multiplied together and another bunch of 2's multiplied together. How do the number of 2's compare? One more in the numerator, right? One more 2 in the numerator than in the denominator. So it just turns out to be, limit is 2 over n plus 1. 0. Convergent. Absolutely convergent. So what? This is, it's like approaching a geometric series with an R value of 0. Right? This is like kind of like getting closer and closer to R value of 0. So that's certainly going to be convergent. Questions on this one? I'm going to hopefully start one more. Okay, here we go. One more. Gotta know your exponents here. Careful. So what does the power on the 5 in the denominator become? 5 to the 3n plus 1? Careful. 3 parentheses, which is 3n plus 3. Do you see it? And then what do we get from the factorials? So this is n plus 2 factorial over n plus 1 factorial is just the same as? N plus 2 factorial over n plus 1 factorial? N plus 2. Because this has n plus 1 factorial in it. It's n plus 2 times n plus 1 factorial. So how many 5s do we end up with, or what does this turn out to be? This limit is? Or it just is. It's not even the limit. What is that equal to? 1 over 5 cubed. 1 over 125. What's the limit? Yeah, so nothing can help this, right? This is n goes to infinity, so n plus 2. So this limit is just getting huge. 1 over 5 cubed is not going to help, right? Greater than 1, this one is. Okay, keep watching Blackboard. We're going to have some written homework as well as web work, okay? So keep watching Blackboard for the assignments. If you have any questions, you can catch me on the way out.